right, so for Unit 2, we're going to start out by learning a little bit about atomic theory, and really we're going to talk about how our idea of what an atom is and what an atom looks like has evolved over time. So this is going to be our first learning target for this unit. So to start off, just a little something to make you feel good. Atoms are what make us all matter. So all matter is made up of atoms. These are some things that we know. All matter is made up of different kinds of atoms and different combinations of atoms. So we know this to be true at this point, but how the heck do we even know what an atom looks like is the question we want to answer here. We know that atoms have protons and neutrons in the nucleus. We know that they have electrons zipping around the outside. So how the heck do we even know that? And how have we developed over time within the scientific community what the atom actually looks like? Okay, so we're going to start by going through some of our dead dudes who have really contributed to our current understanding and idea of the atom. We're going to start way back in 460 BC. We have a Greek philosopher, Democritus. And Democritus he was a philosopher, which means he sat around and thought about stuff. And he decided, and he was really thinking about matter and what it was all made of, what is all this stuff around us. And he said that that matter is made of indivisible particles. Essentially, his idea was if I take a piece of wood and I continue cutting it into smaller and smaller and smaller pieces, eventually I'm going to reach a size or a piece of wood that I can no longer divide into a smaller piece. So he kind of defined this indivisible particle, and he called it atomos. And this is where we get that current day atoms term from as well. So fast forward through history. Now we're in the early 1800s and we have John Dalton. And John Dalton, again, he was kind of sitting around and thinking about stuff. He also did some experiments and he ultimately developed a 5-point theory of what he thought atoms were like. And really he helped to define a little bit more closely or a little bit more specifically what atoms kind of were and define that a little bit better. It took a long time for people to kind of accept Dalton's theory, but today most of Dalton's theory still rings through. There's one point here that we'll talk about that's not 100% accurate anymore based on what we know, but for the most part this theory still holds up. So the first part here, so elements are made up of tiny particles called atoms. So at this point, we know that there are elements that exist. So we have things like oxygen and carbon and nitrogen, and we know that they're made up of atoms. Our second point here, all atoms of a given element are identical. So this is the one where it's a little bit off at this point. We know that they're not identical in all of their characteristics, but they're mostly the same. So all atoms of a given element are identical is what Dalton said. We know at this point then all atoms of a given element have the same properties and have other things that are the same about them. But they're not necessarily identical to one another. In our third part, the atoms of a given element are different from those of any other element. So for example, my atoms of nitrogen are not the same as atoms of carbon, and we hold this to be true as well. If we move on to our fourth component of this theory, our fourth component, so atoms of one element can combine with atoms of another element to form compounds. So this is where we see atoms of carbon plus atoms of oxygen forming carbon dioxide, CO2. And the compound that is formed does not have the same properties as either of the lone elements that originally formed it. So carbon and oxygen are both very different from each other and very different from this compound carbon dioxide. And then finally, atoms are not created or destroyed in chemical reactions. The reaction changes the way the atoms are grouped together, so we can change the arrangement of the atoms, but we don't actually change what's there. And this is known now as the law of conservation of mass. So this is really important, guys. Underline this, put a star next to it in your notes. So the law of conservation of mass says that we cannot create or destroy atoms in a chemical reaction. So if I perform a chemical reaction, I'm going to have the same mass that I started with at the beginning and the end, which means I have all the same atoms at the beginning of a reaction as I have at the end. This is going to be a really important idea when we get to balancing chemical equations. It's important that you understand everything that you put in at the beginning still exists at the end. It's just rearranged itself in some way. All right, so then we move forward. In the late 1800s, now we have our new scientist, J.J. Thomson, and he is the guy who discovered the electron, so this was his discovery. And he developed a model of the atom called the plum pudding model. So here on the left-hand side, this is a picture of a spherical plum pudding. Plum pudding is essentially, it's kind of like a fruitcake. And essentially his plum pudding model said, I have a sphere of positivity. So if you look at this model on the right, I have a sphere and this kind of this positive zone. So we see this big plus sign in the middle. This is all kind of positive aura. And then I have these little negatively charged electrons kind of stuck in there. Present day, we sometimes will hear this model referred to as the chocolate chip cookie model. So if you see that as well, they're kind of the same thing. So plum pudding model, or really we see the sphere of positive charge, and then we have our negatively charged electron stuck in there. So how J.J. Thomson discovered the electron and really the experiment that he used to discover it, again, this is a key point. Make sure to underline it, put a star next to it in your notes. He used the cathode ray tube experiment. So here in this picture, this is a picture of a cathode ray tube, and down below on the site here, there's a video that shows a cathode ray tube experiment. So here essentially we see a ray of light, and this ray of light is negatively charged, but he didn't know that at the time. So there's a ray of light that's shot through a tube, and he noticed that if he put a positively charged magnet near the tube, that the ray would bend upward towards that positive charge. But if he put a negative charge magnet near the tube, then the ray would bend away from it. It would bend down and away. So this essentially helped to discover the electron. So we know that now we have an electron flow through the center of this tube. And he devised kind of what this was. And now we know a lot more about electrons and how they help elements to behave, and we're going to talk more about that in this unit. Again, there's a video below. I would take a look at that as well. All right, now we have Ernest Rutherford. So Ernest Rutherford, going a little bit farther in history, but not too far. He was the one who discovered the positively charged nucleus. So before this, in our plum pudding model, we just had that sphere of positivity with negative electrons kind of stuck in it, like chocolate chips in a chocolate chip cookie. Now, in Ernest Rutherford's model, we see this positively charged dense nucleus in the center, and then we see our electrons existing with lots of empty space around the outside. So he discovered this positively charged dense nucleus, and he discovered that elements are mostly empty space. And the way he did this was with the gold foil experiment. So here's an image of that experiment. Essentially what he did, and again, this is an important experiment you should know, he shot some alpha particles, which are kind of a positively charged little particle, shot some alpha particles at a very thin sheet of gold foil. And what he expected is he expected these alpha particles, because they assumed if the plum pudding model was accurate, that most of them would shoot right back. Or pass directly straight through. But what he saw was something interesting. So most of the alpha particles shot straight through and hit straight on the other side. Some of them got kind of shot to the side here, some of them off to the side, some of them got ricocheted back. And essentially what that showed him is that our atom must be mostly empty space if most of my alpha particles go through, but there must be some dense part of the atom, which is what allows for these ricochets and these bends to happen as well. All right, now in the mid-1900s, we have Niels Bohr. So all of this is happening really within 100 years. So we have a very rapid development in our atomic theory here. So Niels Bohr, he took this theory a step further, and he said, yes, atoms are mostly empty space. Yes, there is a dense positively charged nucleus, and now we know that the nucleus is both protons and neutrons. But he said that, you know what, I'm pretty sure that electrons are traveling in distinct energy levels. And really, he did a lot of experiments with light. And he said that he really developed this kind of orbital theory of the atom. So we have electrons that are existing on specific energy levels or on orbits that are specific distances away from that positively charged nucleus. This is the model in this class that we're going to be using the most. I think it's really the most helpful when we're thinking about chemical reactions and really just how atoms behave in general to be using this model. But it is not the current model that we use in chemistry in the scientific community. We're not going to learn too much about the current model because it's very complicated. There's a lot of physics that goes into it. But I do want you guys to know that it exists. So our current modern concept of the atom, we have our nucleus, which is very, very small. Atoms are mostly empty space. So if we think about if the nucleus was the size of a grape, electrons would be a mile away from it on average. Our nucleus, again, contains protons and neutrons. We know this to be true at this point, and that electrons they are constantly moving around in what we call a cloud around the nucleus. So rather than my nucleus being in the middle, and I know that there's 2 electrons traveling on this perfect, beautiful orbit around my nucleus. That is not necessarily true, even though it's a really nice, simple way to think about an atom. Really, what we know is that there's 2 electrons existing kind of somewhere within this region around the nucleus, but we're not exactly sure where. So that's why we kind of call it the electron cloud at this point. So electrons are kind of in here somewhere, but not necessarily on a perfect, beautiful orbit, like with the Bohr model that we saw in the last slide. So I just want you guys to be aware that there is a more modern concept, and this is called the quantum model or the quantum mechanical model. But we're not necessarily going to learn a lot of details about this one. We're going to use the Bohr model mainly. So here's just kind of a summary. So here we see Thomson's model. This was my plum pudding model. So sphere of positive charge with my negatively charged electrons kind of stuck in there. Then we move on to Rutherford's model. Now we have our dense nucleus in the middle and my electrons just kind of existing around the outside, but we have mostly empty space at this point. Then with our Bohr model, here are my electrons traveling in orbits around the nucleus. And then finally in the quantum mechanical model over here on the right, my electron might be somewhere in this region, but we're not 100% sure where. There's a 90% probability that it'll be kind of in there, but we're not really sure how it's moving necessarily or where exactly it is. All right, so here's just a brief summary of everything. So if we look through our models, Democritus, he thought about stuff. He came up with the idea of atomas, and he basically thought that if I cut something into a small enough piece, eventually I won't be able to cut it into anything smaller. So we basically just have like a sphere or a cube of stuff. Dalton, we had our 5-point theory of the atom. With Thomson, he did the cathode ray tube experiment that helped him to discover the electron, and his model we call sometimes the plum pudding model. Rutherford, he did the gold foil experiment, and he discovered the positively charged nucleus. That's really important. And then finally we had Bohr, and Bohr's model gave us these distinct orbits or energy levels of for our electrons to exist in. This is the one we're going to use mostly, but it's not the current model. Our current model is the quantum model. And really, I just want you guys to be aware that this exists, but we're not going to learn a whole lot about that. All right. If you have any questions, leave them at the end of the video, and I'll see you guys tomorrow.